We manufactured a chessboard set utilizing the UGA Fabrication Lab and at-home equipment to accomplish laser cutting, 3D printing, sand casting, and machining. For the checkered chessboard, we used a laser cutter to etch the chessboard design into a square piece of wood. Choosing a medium density fiberboard, we measured and cut the board to the desired size. We created the checkered design on the Boss Laser software and printed it onto the board. For the chess set, we used a two-step process of 3D printing and sand casting to create each type of chess piece: the king, queen, bishop, knight, rook, and pawn. We inputted existing designs into AutoCAD and designed a schematic for the sand cast mode. When creating the foundry, we made the installation for the steel bucket by mixing water, plaster of Paris and sand, pouring it into the bucket, and letting it dry around a smaller bucket to create a hole for the coals and crucible. The crucible was made of clay graphite to withstand the high temperatures needed to melt aluminum. A 1-inch hole was then cut in the bucket for a small steel pipe to be placed. This served as a duct to provide ventilation to the coals from a hairdryer by providing a constant stream of oxygen to the coals in order to keep them burning at a very high temperature. We created our own version of green sand, similar to molding sand, which was comprised of a mixture of play sand, unscented cat litter, and a tad bit of water. The cat litter's main ingredient was bentonite clay to help the sand stick together. After grinding up the litter, sifting the mixture, and spraying it lightly with water, we were left with a mixture of about 90% sand and 10% clay, firm enough to hold a mold. We created two 12 by 6 inch box frames to pack with green sand, holding half the negative shape of the 3D printed chess pieces. To create the imprint for the chess pieces in the sand, we 3D printed the chess pieces in a half form. We used a small piece of wood placed under the pieces to make an imprint in the sand that would act as the runner and connect the pieces together. A 1-inch PVC pipe was placed on top of this runner wood piece to create the down sprue for pouring. The sand was slowly poured in packs, inch by inch, to ensure the pieces were tightly packed into the mold and would create a tight cast. Once done packing, the mold box with the PVC pipe had the pipe removed. The backs of each mold box were then secured and both boxes were flipped over. Once flipped over, the plywood faces were removed from the boxes. The halves of the 3D printed chess pieces were now exposed and had to be carefully removed to prevent any destruction of the cavity of the mold. Once these pieces were removed, the two boxes were then stacked, placed face to face with the box that had the down sprue on top. This created the entire negative cavity of the pieces inside the two mold boxes. The backing was removed and the molds were now ready for pouring. Once enough aluminum cans were melted down, the crucible was removed from the foundry and quickly poured into the mold. In the first pouring, we quickly realized we did not have enough molten metal to fill the mold. Another issue we ran into was the top molds not staying in the mold boxes and instead collapsing onto the bottom, destroying the negative cavity of the pieces and ruining the cast. To compensate for this, we also tried pouring the metal into the molds without stacking them and without a sprue. This worked. It produced the best results on one side, but did not allow for the entire surface area of the chess piece to be created. Once the metal was cooled, the pieces were then cut into their individual pieces. They were grinded down using a grinder wheel and polished using a brush wheel to create a shiny finish with minimal defects. Delta Scroll was not effective since it did not cut straight lines. so use a table saw to cut the chessboard instead. Perform a test run in the program to see a visualization of the process before etching the board. Prepare more material than needed because you cannot predict the amount of aluminum needed for the casting object and may end up having to repeat the process again. The last sand cast prototypes took 60 to 70 cans. We need the sand to have a stronger hold to prevent it from collapsing. It took a long time to melt, so overestimate the time needed for sand casting. Molten metal cooled quickly when pouring, so work fast. Fire bursts when melting aluminum, so maintain a safe distance and wear welding gloves. There was a lot more slag than expected, so prepare to skim it off.